then just to make it fun, what is the relationship between those two structures? So if they're enantiomers, I could draw a dashed line down and we'd have a mirror image. Are those mirror images of each other? No. So they're non-superimposable. They're not mirror images, which means disastomers. Man, let's just stick with that. They don't have to worry about spelling it. Okay? So that stuff from the stereochemistry chapter will come back. You are expected to be able to compare your products and decide what that relationship is. Okay? Questions about that? Okay. I at least recorded that. I think I'm in the wrong lecture. We'll see what happens. So we could then go through and start to predict things. And we already looked at this, so I'm going to skip over it. I'm going to skip ahead a whole bunch, actually. Yep, I opened the wrong slideshow. Oh, no, it's, I hate the auto open. Okay. Oh, come on. So, we just talked about that. Oh, wow. Okay, so now we're jumping. So, I knew I didn't want to start where I was there. So now we'll... So that's cool. So the stuff that I didn't record was all review anyway. So it turned out well. So where we kind of left off was looking at the addition of bromine. So when we started with the acids, we could see a very clear line or a clear separation. We had H+. The strong acids donated that hydrogen, which then allowed for an acid-base reaction. When we're reacted with bromine, we don't have that strong polarity associated with that structure. Okay? If we look at that bond, probably not a good color to highlight it in black. That bond doesn't have the polarity that we had in the HBr or HCl, okay? Which means our reaction is going to run slightly differently. Okay? One of the things that's nice about bromine or elemental chlorine is they're relatively large, which means their electron cloud is fairly polarizable, which means I can take the electrons from my double bond and push them towards the bromine. Okay? That causes a shift in the electron density around that bond. The electrons push out the other direction, and we end up forming an intermediate, okay? Which we could draw as the transition state if we wanted to, okay, just to get an idea of what's happening here. Very similar to what we saw before. Okay? Except if this wasn't an actual structure in our reaction, we would expect that our bromines could be added on the same side or opposite sides of this ring. We'd get two products. And it turns out we don't get two. They're always added trans. They're always on opposite sides of the ring. They're never on the same side when reacting with bromine. That means that that intermediate, or what we would presume to be an intermediate, can't exist. Something else has to be happening. Okay? And that thing that's happening is that bromine is so large with that large electron cloud that the electrons start to share over with that positively charged carbon, and we end up forming a highly stressed structure with the bromonium ion, a three-membered ring very similar to a cyclopropane, okay, that stabilizes the cation long enough that we end up forming that intermediate. Okay? The repercussions of this, for it to form that three-membered ring, what are the odds that that bond, the last bond there that I haven't highlighted in red, okay, could come in from the bottom? Wrong thought process here. So let's take a look at this bond. Okay, the formation of that bromine cation bond. what are the odds that that electron can come in and attack the cation from the bottom? So what we're saying is if this corner of the iPad is the cation, so we've got the positive lobe of our p orbitals, both lobes. Our bromine is here. What are the odds that that bromine can form a bond back that direction while still maintaining the up and the down?
Why would it?
Okay, so why would it? We're just looking at possibilities. Is it possible? Probably not. Why?
Because you're emphatic about it.
It's a really weird angle. You have to have a bond going up connected to an atom that has also got a bond going down. One of those bonds is ridiculously long to connect the structure. Okay? We'd have to build a U shape within it to get that structure to occur. Okay? Which just isn't physically possible. Okay, so what I'm asking, here's our p orbital, there's the bromine. To form that cyclopropane-like structure, we can take these electrons on the bromine and share them with the cation. Do I share them with this lobe or with this lobe? The one on top. Is it physically possible for me to share them with the bottom one?
No.
No. I'd have to do a rotation about that bond. The ring prevents that. There is no way for that bond to form across. Which means that if I look at my cyclic structure with the bromine, it has to form like that, above our plane. Which means if we now look at the bromide, where does that bromide come in and alleviate that stress within the ring? Can it come in from the top? Why not? There's too many electrons there. There's a steric blocking preventing that top attack, which is why we can't get the bromines adding on the same side of the ring. The electrons from our bromide have to come in from the bottom. Okay? Which means one bromine is aimed up and the other bromine is aimed down. If we were going to look at this on our structure, we're going to draw out our product, we get a wedge and a dash. Okay? Does that make a little bit more sense about where or why we were looking at that? Okay? The idea is to recognize that in this mechanism we have to get that anti-addition. We end up with the trans product. We cannot get the cis bromination product using this reagent. Okay? Does that make sense? We then looked at the reaction with hydrogen. Remember how I said that I was going to show you a picture? I like your textbook's image a lot better, which is why I've referenced it down here. I think it has a better image than what I've got. But I don't have access to the textbook images, so I can't do anything about that. We'll look at our catalyst surface, which in the case of the reaction with hydrogen, we're looking at platinum, palladium, or nickel. Any one of those. It doesn't have to be all three. Okay. Our hydrogen comes in, coordinates to the surface. So the platinum facilitates the electrons in that hydrogen bond sticking to the surface, and we end up with kind of a weak pseudo-cyclopropane or butane structure. Okay. Our alkene also comes to the surface, and the electrons in the double bond start to coordinate to the surface as well. Okay, so what we end up getting is something along these lines. Okay, now in our lower left. The alkene and the hydrogen molecule will float around on that surface until they encounter each other. Okay, and this is where platinum facilitates the transfer of electrons from our hydrogen over to our carbon. At that point, I don't have electrons that I've got coordinated to the platinum surface. So what happens to the carbon and the hydrogen? They lift off of the surface. Okay? we still have the other carbon bound, we still have the other hydrogen bound. Okay? Both of those species are extremely reactive, so they'll try and stabilize as fast as they can, and that's where your hydrogen and your carbon will meet up, and your final product lifts off. Okay? The important aspect to see in this is that if we look at our double bond, let's label this red, and label this back one green. Where's the red atom in our product?
Coming towards us.
Yep, that's not red. Okay, because of how the geometry of that system aligns. So our red atom propagates to here, our green atom is the one in back. Our hydrogen comes in, the red atom lifts off the surface. Okay, so if we color our red all the way through, see if I can mark it. Okay, there's our red atom again. Once the double bond is coordinated, it's stuck. It cannot pick up and flip around. Okay, the next part is where the next part, I don't think there's an undo. No. Man, they need to add that. So let's go through, highlight our red atom. The next part is looking at that green atom, which I now have to go back through and color. Green's a really bad choice. Let's try blue. Okay, there's our blue atom in back, our blue atom there. Come on, stop selecting. Okay, can you see our blue atom that I'm now stabbing at? Back there. Okay. Where is it in the next step? It's still the one in back. Okay. And if we look at our final product, it's also still the one in back. Okay. This reaction happens so fast that we never get rotation around that bond. Okay, that does not occur. Which means that our hydrogens end up getting added on the exact same side of the double bond. So if we were going to refer to the addition, we could say this was a syn addition of hydrogen, resulting in the cis product. Okay, or our hydrogens being cis in our product. Okay? Is that the same or different from the bromine reaction?
Different.
It's different. Our bromine reaction added trans. Okay? So it comes back to the mechanism and understanding that. Based on the question asked, you might need to describe the mechanism, or you could have memorized that when you add bromine to the reaction or to a double bond, the bromines add trans. I'm fine with that. If you want to spend your time memorizing everything, that's okay. Okay? Ideally, I want you to be able to look at the reactions and follow where the electrons are moving and what's occurring with these. Okay? So that we know that bromonium intermediate prevents the syn addition. Okay? So that's our reaction with hydrogen. We're going to draw out a generic reaction here. Way in black, yes. This is where the slides are going to snowball. If we start with our alkene, we add our hydrogen. What else do we need for hydrogen to add across the double bond?
I have a quick question.
Yes,
So
go
will
ahead.
the large element always be trans product?
The bromine and chlorine additions, yes, generate trans products.
And if it's just a little molecule like hydrogen? Will it be cis,
In
or is that
these
not
mechanisms, it follows cis, yes. So you have to go based on the mechanism of that reaction.
Okay.
So what I've shown you so far, you're absolutely correct.
So if we look on a test and we see chlorine, we can automatically say it's trans?
Yes.
Okay.
Does that work?
Mhm.
Okay. So Adding hydrogen to a double bond. Can I just add it? No, what do I need?
Catalyst.
What catalyst do I want to use?
We just use the platinum, whatever it was called.
Palladium.
We could use platinum, or we could use palladium, or we can use nickel. Okay? Any one of those. Or if you want, you can write them all down. I'm fine with that too. What would our product look like? Did we do anything to the sigma bond structure?
No.
Nope, so we'll leave that alone. Is that our product? What's that?
Yeah.
Yeah. We added hydrogen to the double bond.
And then you don't.
There's your product. Do we need to specify the location of the hydrogens? No, why not? What's one of our organic simplifications? Implied hydrogens. We don't have to specify it. Okay? For your sake, let's go through and add those hydrogens. Or add, let's say, here we go. 2 methyls now. Okay, where are those 2 methyls? So we could go and draw this. Would that get you full credit? No, why not? You have to specify how the hydrogens came in and reacted with that double bond. The hydrogens were added cis, which means how are the methyls on there? They also need to be cis. How do I specify that they're both cis? I can give them both wedges, or we could go through and give them both dashes. Okay? Does that make sense? If you don't like implying hydrogens, that's fine. Go through and draw on the hydrogens. It's okay. Okay? Questions about the hydrogenation? Okay? The next thing that we can look at in this, well, actually before we do that, let's look at that reaction a little bit closer. What did we add to the double bond? Hydrogen. What type of reaction increases the number of hydrogen bonds? Reduction. We've also performed a reduction reaction. So we could classify that as a reduction. Okay? Other important aspects, we've got the syn addition or cis product. Okay? From our reduction reaction. Okay? Of course, if we can do reduction, what else could we likely do? Oxidation. So let's take a look at that second reaction down below. So we take our alkene and we react it with osmium tetroxide. Where is osmium on the periodic table?
Not where we usually are.
Not where we usually are. Okay? So what are the odds I'm going to expect you to know the mechanism? I'm not going to expect you to know the mechanism at all. Okay? Largely 2 because I have no idea what it is. Okay? But I have some concept of what's happening in it. The osmium tetroxide, that molecule, interacts with the double bond, resulting in what kind of an addition? So officially we would actually not say cis, it's syn addition. Okay, or a cis product. Okay. The other fun thing about that, osmium, that's way in the middle of the periodic table. It's not one of the elements we're concerned about, so we're probably not going to keep that structure around. That's not a particularly helpful thing to have. So what do we end up doing? We run a second reaction. So we can break it into 2 individual steps of the reaction. And in that second reaction, the osmium tetroxide is cleaved from the structure in such a way that we end up forming what's referred to as a diol. Why is it a diol? Wow, okay. Yeah, good job. We get 2 alcohols attached to that. Notice the stereochemistry. How are the alcohols added to the structure? We get our cis product and we could say syn addition.
So those two just go hand in hand.
Yep. Like I think I said this on Tuesday, it's kind of like an adverb versus an adjective. The cis is describing your final product, so I would call it an adjective, and syn is describing the action of the reaction. Okay? What's the net result as we move from our alkene to our diol? We added oxygen bonds, so we did an oxidation reaction. Okay? Yes? No. And the reason being is you aren't reacting with hydrogen ion.
Oh,
Yeah. Okay? Questions about that? Okay. That's pretty much the end of chapter 5. I'm pretty sure. Let's take a look at the second page here. Yep. So there's one more reaction that we'll cover from chapter 8 and then call chapter 8 pretty much done. And that's looking at the formation of a new functional group. That new functional group is referred to as an epoxide. Okay. Epoxides are three-membered rings of this format. So we've got 2 carbons and a single oxygen. Okay. What can you tell me about the potential reactivity of an epoxide? Would we expect it to be highly reactive or not really reactive at all? Highly, okay, why? What's the hybridization on our carbon? sp3, which means the bond angle needs to be 109.5. What's the bond angle in an equilateral triangle? 60 degrees. So we've got a lot of ring strain on this structure. It's really dying to pop open. Okay? So epoxides are nice because they're fairly reactive, and we can end up producing some other interesting products at the same time. Okay? This came from chapter 8, which was our alcohol chapter. So what do you think one of the products of the ring opening is going to be? An alcohol. Okay? So before we even get to the alcohol, though, we have to know how to form the epoxide. Okay? So we have to somehow force 2 carbons to share their electrons with an oxygen atom in that kind of weird bridging system. Okay? It's not the easiest reaction. To do that, we need to generate a really reactive oxygen species. Okay? That is found right here. Anybody know what kind of bond that is? What that's referred to? Particularly if I did maybe something like this. That's a 2. Peroxide. H2O2 is peroxide, or hydrogen peroxide. The bond between, or the part that makes peroxide so reactive, is right there. Your oxygen-oxygen bond. Okay? If we go in and look at the peroxide, eraser. If we go in and take a look at the peroxide that we're working with here, we still have that oxygen-oxygen bond. It's fairly weak. We don't get the polarity associated with that as much. That bond can fall apart given the right circumstances. Okay? We need something to help push that along. What we're going to end up using are the electrons in your pi system. Okay? This is going to involve a lot of arrows. I do not expect you to have this mechanism memorized or know how to draw it out. Okay? But I want to show you just so you can get an idea of how complicated these things can get. Okay?
So is this gonna be on the test?
You are responsible for knowing what this reagent is, which I'll give you a name of it in a second, and how it reacts with double bonds. And by how, I mean you take this reagent, you add it to a double bond, what do you get? You get an epoxide, not the alcohol yet. Okay? So how does this reaction work? Let's make sure I can do this right. We're going to take the electrons in this bond. Where do the electrons spend most of their time in that bond? Close to the oxygen. So oxygen says, you know what, hydrogen, I'm going to take the electrons and I'm going to share over here with that carbon. What happens to that carbon now? How many bonds would it now have? Too many. So what do? We're going to have to break the bond. So we're going to take the electrons from that bond, we're going to give them to the oxygen. But now the oxygen has too many electrons. So what does the oxygen do? So it breaks another bond. Those electrons have to push away from it. But what happens to this carbon now? Also has too many bonds. So what do we have to do? We'll have to break a bond. The electrons on that carbonyl can come pick up that hydrogen. And if we go through all of that to figure out what happened, okay, actually, since I've got colors, let's go ahead and do it. Bonds that formed. We'll start with our first bond. There's our blue bond. That was our very first arrow. Our second arrow. There's that bond. What happens to, I'm going to do it in yellow, the yellow bond? Does that exist any? Well, actually, we can show where that goes. Where does that bond go? It forms the double bond. Okay. Where does, so that was this bond in electrons. Where does, what do we get? What color do I need? Let's go orange. Where does this bond and the electrons go? To that hydrogen. Okay? So we can follow where everything went. It's just a big mess. There's all sorts of electrons floating through that. Again, I don't expect you to have that memorized. I want you to know where it's coming from, though. Okay? So as far as what you're responsible for, if I give you a peroxy acid, which is this guy here, how do we know it's a peroxy? We see the O-O bond. How do we know it's an acid?
OH.
Not quite. An OH would be an alcohol. How do we get a carboxylic acid? There's our acid portion. There's our peroxy portion. And the hydrogen's just chilling. Okay? So if you see that functionality, you should immediately be thinking epoxides. It's going to react with a double bond to form that epoxide product. Okay? Did we do anything to the rest of that ring? Any of those carbons perform anything in this reaction? No. Which means when we drew out the product, it didn't matter, or we just have to draw them there unchanged. What if I had instead given you this? And I said we react this with another peroxy acid. Let's just draw it like this. What's your product? What's that? I'm going to have my carbon, my epoxide ring. What else? Hydrogen's where? I just want to make sure. On the rest of that structure. So in our first case, we didn't have just hydrogens, we had carbons there. They didn't perform a role, so they just continue to cross. When we change the structure and we change them to hydrogens, we just add them in there. Okay? Kind of makes sense? So let's clean it out again. Let's try another one. Let's do... And I'm going to react this with a peroxy acid, but instead of actually saying peroxy acid or drawing that out again, the most common peroxy acid that you'll probably see, MCPBA. Okay, so that's the most common one. So let's say we go through this reaction, except now here's our starting material. It's this alkene. What's our product look like? So we need that ring. So there's our carbon, carbon, there's our oxygen. So there's our epoxide. And we also technically still have our hydrogens on there, right? Questions about that? Okay, this next question I'm not going to test you on the exam, except maybe for extra credit. Are we concerned about stereochemistry? Should we be concerned about stereochemistry? Is it marked? What's the relationship between this CH3 and that CH3? They're trans, which means when we move to the product, what's the relationship between those two have to be? They also have to be trans. But we're in a three-dimensional structure. We've got sp3 carbons, which means what would we use? Wedges and dashes. So if we draw this one on as a wedge, the other CH3 has to be dashed. Okay? So stereochemistry can be a problem. It will constantly come back and haunt you. Remember that it's there. Okay? When it comes to the epoxides, I'm not going to directly test you on that. Okay? But realize you will probably see that in the homework problems, maybe. Okay? Do we understand epoxides a little bit better? Okay, I heard some yeses, some nos. Enough yeses that we'll move on. Okay. What we can now do with the epoxide is take that a step further. Once we've got that epoxide, it's a highly strained ring. Okay? So what we're going to try and do is mess with that highly strained ring. Okay? So there's a couple reasons it's highly strained, and we addressed one of those. What was that rule or reason? The bond angle. What else might cause this ring to be really reactive? Right idea with the lone pairs, but not quite. If we drew out an alcohol, what would you tell me about its reactivity? Remember, alcohol has had a million different things for reactivity, right? So why'd you do that? What would you tell me about that carbon in the alcohol? It's partially positive, meaning it is electrophilic. If we go back and look at our epoxide, do I have a carbon-oxygen bond? Yes. So what's special about that carbon? It's an electrophile, which means our epoxide can be extremely reactive with nucleophiles. How can you tell if it's a nucleophile or not? So what we're looking for is anything that is negative or lone pair electrons. Okay? So let's take a look at a negative charge. Let's pick something relatively simple. Let's say OH minus. What would our product be if it reacted with the epoxide? Did we do anything to the sigma structure? Nope. Did we do anything to our epoxide ring? Would we expect that ring to fall apart? Yeah. We're going to take our hydroxide and attack that carbon. How many bonds does that carbon have? Too many, so we have to break a bond. What bond do we break? Why the carbon-oxygen bond? You're right.
Because that's the strength one.
It's the weakest one. Why? All the other ones have the same angle.
Because it's close to the other.
Because of
Difference in electronegativity. Oxygen's more electronegative, so it can take those electrons. What ends up happening? We get RO minus. Jeez. Try and zoom in and make that look prettier. That was. We've got our negatively charged oxygen because it picked up electrons, and then we would have NOH from our OH that just attacked, our nucleophile. You guys see it? What's the relationship between those two oxygens? Is this a chiral center right here? How about this one? What does that mean we need to specify in our product? Wedges and dashes. What's the relationship between those two? Look at the reaction. RO minus had to come in and attack. Did it attack from the top side of that ring where the other oxygen is, or did it attack from the bottom side? Bottom side, which means we would draw this as what happened to the electrons, or what happened to this bond then? That would then be wedged. And we end up with our trans product. What if I went through and changed this? Instead of OH minus, I think OH minus is a terrible nucleophile. Let's make it, I personally think, cyanide. What's the product now? Does the cyclopentane structure change? Or sigma structure up here? No. So that's still the same. Where's that CN minus attacking? From the bottom. So what happens in our product? What would we expect instead of OH? We would expect what happens to the bond that had the electrons in that oxygen? Goes the oxygen again, right? Which means we get O minus. I don't like cyanide, so I'm going to cross it out. So instead I'm going to pick methylthiol. What happens now? What's our product look like? Same as the other one. That's exactly what I wanted to hear. A very angry sigh of same as the other one. It's actually true. That's what I wanted to hear. The reaction doesn't change. I can put whatever nucleophile I want. I get the exact same reaction. Okay? And that's one of the things that throws people for a loop. If I change that nucleophile, now everybody says it's different. It's the exact same thing. Look at the reactivity. We're looking for something that's negative. How does that negative react with the epoxide? It reacts because that carbon is electrophilic. It's partially positive. The ring structure opens. Okay? So it's the same patterns over and over and over again. Okay? It doesn't change. The only thing that changes is our perception of it. So try to avoid getting bogged down in memorizing the exact details, and instead memorize your positives and negatives and how those things can collide. Does that make sense? Okay.
Oxygen always a negative?
In that case, yes. How could we then fix that structure? Because that's not a particularly happy structure being negative.
Some electrons.
We don't want electrons.
Give it a hydrogen.
We could give it a hydrogen. So we could do a workup of this reaction where we add some kind of mild acid. That acid would protonate our alcohol, or protonate the oxygen, giving us our alcohol. Okay? Questions about that? Okay, that was the case of a strong nucleophile. We looked at something that was negatively charged. What happens if I don't have a strong nucleophile? Let's say I add methanol. What happens in this case? Right, we end up getting no reaction. Why is there no reaction? This may be a... do we have electrons? Yes, so we still have electrons. It still can act as a nucleophile. Okay, this still lacks electrons, so it still acts as a electrophile. Okay, but we don't have anything really pushing the reaction. We don't have very large charges. Everything's already neutral. There's nothing to suggest this reaction is going to push forward. Remember, when we try to get a reaction to go, we try to add something as reactive as possible. We added strong acids, okay? Or we add a structure that's highly polarizable. Oxygen is very, very small, okay? So we don't have that reactivity. How can we get methanol to react with this structure? Okay, heat's a possibility. That can weaken bonds, but we want to maximize our yield. Ultimately, what are we trying to do? We're trying to break our carbon-oxygen bond. How can I make that bond more inclined for those electrons to go towards that oxygen? What would make oxygen more willing to take electrons away from something?
Make it positive.
Make it positive, exactly right. How can I make that oxygen positive? When is oxygen positive? How many bonds does it need to have? 3. So if I put another bond on there, that oxygen becomes positive. It's now activated so that my weak nucleophile can attack. What bond do I put on there? It's got to be something easy, because if I do carbons, carbons don't like having charges. It's not going to be easy to put on there. What could I add? I can put a hydrogen on there, which means when I react with a weak nucleophile, I'm not going to add just the nucleophile, but I'm also going to add H+, a source of a strong acid. Okay? That strong acid will activate the epoxide oxygen, facilitating the ring opening and us continuing the rest of the reaction as shown.
What would make that H plus react with that oxygen as opposed to the oxygen of the weak nucleophile?
That's a very good question. And the answer you're not going to like. When we're looking at these reactions, we're looking at very large concentrations of everything. And what ends up happening is, yes, that nucleophile will pick up the hydrogen every so often. But the hydrogen can come on and off fairly rapidly. When the hydrogen comes on to methanol, methanol's not reactive. It can't do anything with the hydrogen on it except get rid of the hydrogen. What happens when I add the hydrogen to the epoxide, though? It makes that bond more active. Now something else can come in and attack and react with it, causing that bond to break. Okay? So when we add that strong acid, you're right, that attacks all things that have electrons, including our nucleophile. Okay? But our nucleophile is in a state where it's not very reactive. If it picks up that hydrogen, our electrophilic structure, our epoxide, is a lot more reactive. So as soon as we acidify it, it can continue on to the next step. Okay? And yeah, that's a very tricky question. Are you guys done drawing it? I'm seeing some people continuing to draw. So I'm about to hit next. What's that? Okay, fine, I'll draw the product. This would be our first product. Is this structure stable? What's going to happen? In fact, I'm not even going to draw that. The oxygen will take the electrons back from the hydrogen, and we end up with our final product, an upside down U. Okay? The removal of that hydrogen is a very fast step. Okay? It's something that you should have seen already when we looked at the SN1 mechanisms. Okay? At least the homework had you do that a bunch. Okay? So, how can we end up summarizing all of this? Okay. If we take an epoxide, so we're looking at another epoxide, and we can look at two different conditions that this reaction can run in. If we run under acidic conditions, we're going to run in an SN1 type. I'm just going to say it, but I'm not going to expect you to know it. It's going to run in under SN1 type conditions, and you'll notice that your product ends up being slightly different than if we went with a strong nucleophile or basic conditions. Okay? The reason being is that if we acidify that hydrogen, what happens to the bonds next to it? We've got two bonds for possible attack. In the previous structures, when we looked up above, we've got those same two bonds. When we looked at it just a little while ago, what's the difference between those two bonds? Rhymes with thing.
Nothing.
Nothing. Sorry, I'm back to the bad rhymes. What's the difference now in our lower structure? Is there a difference between those two bonds?
Yes.
Yep. What's that difference?
Something.
One's red, one's blue. Want to work with me, right? What's further different about it? If we had the red one take the electrons, what happens to this carbon? Becomes positive. If we had the blue one take the electrons, what happens? What happens to this carbon? What can you tell me about this positive? Keep going. It's tertiary. It's a tertiary cation. What about the red one? It's secondary. When our ring, and if we're looking under acidic conditions, which of those bonds is going to break first, our red or our blue? The blue. So that we can form our tertiary carbocation, which means where does our nucleophile attach? At that position. Ooh, that was terrible. Ignore that one. That one's bad. Okay? So our nucleophile comes in from the backside and attacks that position. We still get our trans product of the nucleophile and our alcohol. What happens under basic conditions? Do we have anything activating that alcohol to bond, or that alcohol carbon bond to break? Still just an oxygen. What do we end up reacting if we're under basic conditions? We have to have a nucleophile, and in this case a strong nucleophile. What's a red flag for a strong nucleophile? Negative charge. That negative charge is going to come in and react with one of those carbons, either our red or our blue carbon. Which one's going to be the easiest for that negative charge to interact with? The red one. Why? Less sterics. Under basic or neutral conditions, we're looking at an SN2 type reaction. Under acidic conditions, we're looking at an SN1 type reaction, which ends up changing where our nucleophile attaches. So if we look in our neutral or basic conditions, our nucleophile attaches to the other carbon. So we end up getting different products depending on the conditions that we put into this reaction. Okay? We just talked about that for both of those. Okay? Last thing I kind of want to do, I think, before we end for today is our alkyne reactivity, because officially we're supposed to talk about it. So we can draw out an example alkyne. We're looking at the triple bond. If we compared that to our alkene, we've got our double bond. What changes have happened? What's changed about my carbon? How about the hybridization? In one case, it's what? Sorry, the first case, it's sp. In the second case, it's? Okay. What does that mean about the reactivity of the atoms attached to it? So in particular, we're going to look at the carbon-hydrogen and our carbon-hydrogen. What bonds or what orbitals are involved in making that bond? We get an sp hybrid from the carbon, and from the hydrogen we get an s. What do we get in this bond? You get an sp2 hybrid from the carbon and an s from the hydrogen. Why does that matter? What's the difference between the s and the p orbital? sp, not quite more reactive. It's coming back to where the electrons are. Where are the electrons in an sp orbital versus an sp2? Closer to the nucleus. What kind of element or what kind of description would you say about that element if it's drawing its electrons closer towards it? It's more electronegative, which means what about that hydrogen? It starts to become, if the electrons in here start drawing that way, we get a partial positive. Okay? Why is that important? That difference in electronegativity now, or that change in hybridization, changes the electronegativity enough that the alkyne carbon-hydrogen bond is acidic. Okay? So we can react alkynes with really, really strong bases. Okay, so if I add a good strong base, okay, what's a good strong base? Try that again. Sodium hydroxide. Turns out sodium hydroxide is not a strong enough base. So we'll move to sodium amide. Okay, sodium ion does what in most reactions? Dissociates, so we can ignore it, and really what we're looking at is our negative charge. Which is the stronger base, hydroxide or amide? We'll draw up hydroxide real quickly. Which is the stronger base? Figure out base strength. What's the first thing we should look for? Negative charge. They both have negative charge. They both have negative charge, so we move on to the next thing. Size is pretty important. Is there a difference in size between oxygen and nitrogen? Nope. Move on to the next thing. What's the next thing? Electronegativity. Okay, which of those elements has a different electronegativity? Or do they have different electronegativities? Yes. Which one's more electronegative? Oxygen. Electronegativity is the measure of what? So draw electrons towards it. Okay? For it to act as a base, what must it do? It must share electrons. Which one's the stronger base? NH2, because it's less electronegative than our oxygen. Okay? So what can end up happening is the sodium amide can share its electrons with the hydrogen. We can push our electrons onto that carbon, putting a negative charge on our carbon. What kind of a species have we just made? Yes, there's tons of answers on this one, and I expect to hear them all. What's that? Anion, good answer. Not one I was looking for, but that's true. What did we say sodium amide was? A base. Why did we say it was a base?
The sodium dissociates
And left what?
and left a negative charge.
Negative charge. What does this species have?
Negative charge.
What can this species act as? Bronsted base. What else could it act as?
A nucleophile.
We've got a nucleophile because it could donate its electrons to an atom other than hydrogen. What else could it do? Try again. Lewis base. Donate its electrons. Okay? So we took a structure that was relatively unreactive and we converted it into something that is now extremely reactive. Okay? So I expect you to remember and acknowledge that your alkyne structures, your terminal alkynes, which means you've got a hydrogen attached to the carbon, that those hydrogens are acidic and we can react them with a very strong base. It has to be sodium amide to make a nucleophile. Okay? How could this be important? Well, now we can start to string together reactions. I could say, given an alkyne, how can you make some other structure? Okay, well, you could connect that alkyne to another structure, okay, by turning the alkyne into a nucleophile. You could then react it with an electrophile. What else is special about the alkyne? What kind of bonds do we have in the alkyne? We've got sigma bonds and, you said pi, not 5, huh? We've got pi bonds. Where else have we seen pi bonds? In the alkenes. What did we just spend the last 3 lectures going over? Alkene reactivity. How do you think the alkynes are going to react? Pretty much the same. Okay? We just looked at the acid-base reaction. So let's pick another example here. So I don't think I want to get into chapter 9. Let's take a look at this alkyne. What happens when I react this with sodium amide? Sodium amide is what kind of a structure? Or what kind of a compound? Strong base. So what do bases want to react with? Acid. What makes a structure an acid? Has to have hydrogen. Has to have hydrogen attached to an electronegative element. So let's go through and look at our other structure here. Do we have a hydrogen attached to an electronegative element? No, we've got hydrogens attached to the alkane, not the alkyne portion of this structure. So what's the answer in this case? No reaction. Okay. Let's try coming up with what do we react? So this is definitely a harder one. This requires at least 2 steps. Bromines. So ultimately we could see a bromine bond breaking. Not a bad idea. Anything else? There's a bunch of bromines. How could I add bromine to a structure? What would I add bromine to? An alkene. Okay, or a pi bond. But I see another 2 bromines. Which would mean I broke another pi bond. What kind of a structure has 2 pi bonds between 2 carbons? An alkyne. What are we starting with? An alkyne. Okay? But are we missing something else? The answer is yes. How about the rest of this ring? Was that in there yet? No. So somehow or another we have to get our alkyne to bond to that ring first. Okay? Can I get the alkyne to be reactive at all? What would I need to do? Is this hydrogen particularly reactive? It's partially positive, which would mean it would act as an acid. What do we need to react with acids? Base. So we're looking at an alkyne reacting with a base. What base do we have to use? It has to be the sodium amide. NaNH2. What's that?
Partially positive.
What?
Why is it partially positive?
The hybridization of this carbon changes the electron density in that bond enough that the carbon becomes more electronegative. Okay? What happens in this case? We now generate this as a product. What's special about this structure? Highly reactive as what? A nucleophile. So we've got a negative charge. Where's this carbon in our product? We just said that carbon's a negative, which means what does this atom have to be? Positive. So I can react this species as a nucleophile, which would mean I need to react it with an electrophile, which means this carbon needs to somehow be partially positive. But we can't add anything that's starting charged. So how can I make that carbon positive while still keeping it neutral?
Double bond.
Give it another bond to what? The double bond makes it trickier. Okay? Is carbon going to take the electrons away from hydrogen? Or sorry, give up its electrons to hydrogen? No. So hydrogen doesn't work. Give me another element. Oxygen could work, except when we add oxygen, we also have to add that H. What's the problem with that hydrogen? It's acidic. So an OH doesn't work. What else could we add? We could add a halogen or bromine. Bromine takes the electrons away from that carbon, making that carbon partially positive. So what can happen? We can take our nucleophile's electrons and attack that carbon. What's the result of that product or that reaction? Justin, what did you say earlier about those red and green bonds?
They broke.
They broke. Those came likely from bromine reacting twice. So we would run our twice the amount of bromine in this reaction. Okay? What you're responsible for is knowing the reactivity of each of those species so that you can go through and build this kind of map and slowly start working your way through it. Is it ridiculously difficult? Absolutely. Okay? How do you do it?
You just take the hit on the test and move on.
That's an option. That's fine.
Back to it if you have time.
How did we go through and approach it this time? We looked for the most reactive bonds. Bromines. Good call. Where have we seen bromines added in pairs? Br2. What does Br2 add to? Alkenes is a possibility. Or
Double pi bonds.
pi bonds. Do we start with pi bonds? Yes. So if we can somehow get our pi bond attached to this structure, we can react it with bromine. So we figured out the tail end of our part. We knew that this had to be here. Okay? Which then means we have to somehow get this ring structure attached to the alkyne. So we then have to evaluate the reactivity of our alkyne. Can we make that alkyne react with a ring structure? Well, if we remove the hydrogen, it becomes a nucleophile. If it's a nucleophile, I can react it with an electrophile. And what type of a reaction? Substitution. Acid-base. Substitution. Whoops. Let me follow my arrow. Acid-base, substitution, followed by addition. All three reactions we've looked at this semester, you should know the mechanism for all three of those reactions. Okay? You can expect a 3-step prediction on the exam. That will be the hardest version of it. How should you approach it? Exactly as we just discussed. Identify where there's differences in electronegativity. You need to know the reactivity of the functional groups. Okay? This is why that very first assignment, when we handed out the functional groups, I said you need to know Lewis acids, Lewis bases, electrophiles, nucleophiles. Okay? The rest of this semester is one reaction after another. You now have all of the fundamentals. You have to start putting them together. Okay? Yes.